Hello everyone. In this video we are going to investigate more about parametric differentiation. We want to see what parametric differentiation is and how to find derivatives of parametric equations. Before that, of course, it is a natural question what at all parametric functions are, because when we speak about differentiation, that means we speak about functions. So that is what we are doing, and therefore it is important to have some insight about parametric functions. So important processes which are in modeling represented as curves in the coordinate plane must be represented using parameters and two functions of the same parameter. In order to study those processes properly. So in some later videos we will see concrete examples of why is that important, but such processes for now where we must use parameters and two functions of the same parameter we call parametric equations of the curve. So parametric equations of the curve in the two-dimensional coordinate plane are given by x equals x of t and y equals y of t, where t is that parameter and t is between in some closed interval ab. And this will then represent a curve in the coordinate plane. For certain values of t. The most common example is that one of the circle. That's the first and the most common example, the parametrization of the circle, where we have x of t equals cosine t and y of t equals sine t, and t goes between 0 and 2 pi. This represents the parametric, this is parametric representation of the circle. Now this is not a function because the values are not uniquely determined, but if we have, for example, x of t equals cosine t and y of t equals sine t, and t goes between 0 and pi, Then this represents a function, and this is upper half of the unit circle. So I will just put here, it is meant unit circle. So exactly what we have said above, we have a parameter t, okay, that goes between 0 and 2 pi, and we also have two functions, x of t and y of t. So those are two functions, and notice that we have one and the same parameter for both functions. Another example of the parametric equation, so many examples are there. If, for example, so example 2, we have x of t equals 2t and y of t equals 4t cubed, and then t is between, let's say, 0 and 1. Usually we will not go into the details because we are mainly concerned about the rules for differentiation in this context. But how we can understand is that we can make a table and here we have t, here we have x of t, and we have y of t. And then we start for some values of t, let's say 0, 1, 10th, 1/3, 1/2, 3/4, and then for each that value we find the corresponding points. And then we plot those points on the coordinate plane. Then from there we can see how the curve approximately has the shape. Of course, the usage of technology here is of advantage and it's essential. But we can do, for example, here will be 0, 0. So the point 0, 0 is on the curve. Then 1/10, that is 1/5 on x, and 4/1000 on y-axis. So that means that 1/5 and 4/1000 is on the curve. Then we have 2/3 and 4/27. So the points 2, 3, 4/27, and so on. So we have some points, but the question is how exactly does this curve look like? And many other features. So in order to plot, in order to graph this curve, we need to know where it has minima or maxima, inflections, and so on. And for these things, we need derivatives. That is how derivatives come into the story. So we need to find derivatives of these functions. Okay, so the formula is the following. It is basically the formula for the derivatives of composite function, and what we want actually is dy over dx. So knowing that x is x of t, y is also the function of t. And again, we want the derivative by t. So here is done like a trick. We basically just divide by 1, so dy over dx is. Now, these functions here are differentiable. So we can just do dy over dt and dx over dt. So it is supposed that these functions are differentiable. And then here it is actually meant as dividing by 1. So if you look carefully, so dy over dx is the same as dy over dx times 1. And that is dy over dx. 1 we can write as dt over dt. So that is here. That's now equal to dx over dt and dy over dt. And this is the essential formula that we need for, so formula for differentiation of parametric functions or curves. And we will see some examples.